This is The Road to Reality, a complete guide to the laws of the universe, Roger Penrose, written by Roger Penrose, who won the Nobel Prize this year. I'd like to congratulate him. And I'm not so good reader, good at reading books, so I just partly read this book, but it's very interesting. So literally, this is the road to the reality. What's reality? At first, my concern is what the reality and what the laws of nature and what the relationship between laws of nature and myself and us. And unfortunately, I'm not like a genius scientist that I don't find laws of nature through my inside, the inside of myself, but through working at a job of the technical job and mass production job, designing small analog circuit job to digital circuit like memories. There's already build up. There's already the environment build up in the world. In here, also in Japan, and Taiwan, Singapore, and the United States, and China, and Europe, and Australia, everywhere, in communicating in conjunction with these environments to connect the fiber cable, and the information is shared in a flash in these days, and the environment is there, and we don't need to make an experiment, make an instrument, build up an instrument ourselves, but 100 years or more ago, they need to build up environment, measurement systems, equipments. They need to construct experiment and try and error, trying error, and all of the effort through their life makes our environment now. And environment comes to me. First environment existed. Me comes after that, and experience. Not directly to the nature, indirectly to the nature or the constructed environment, and I recognize what the reality of piece of the reality of the nature, piece by piece, and reconstruct the reality image of nature myself. From that system. So my concern is road to reality, actually. My concern is reality of the nature, but the road to the reality is very indirect. But the good science, I think, we need to uh, direct make a direct interaction to the nature, uh, the reality, making own instruments to measure or observe something you mentioned. And that is the basics of the philosophy and thought of human being to access the nature. So every people experience indirectly can experience indirectly the nature of law, or but if you don't mention intentionally, if you make that unintentionally, deal with the system unintentionally to look at the nature, the face of nature, you couldn't touch any nature aspect, any reality of nature. Sorry. We can get the piece of reality aspect of nature only when intentionally dealing with the environment system. I mean, there's no electron exists, and we can't see ultraviolet light, and we can't see the gravity, and we can't see the how the molecules are connected, and polymers are generated, and we can't see the polymer in the neighbor eyes, and anything else. We only when we can access to that aspect of nature, after running many concepts, and to run many concepts, a lot of concepts the earlier pioneers built is tedious work, so it needs a lot the eagerness for it to almost eating something I like to eat. I want to eat, drink, like so. Passion like this. What to say? You know, just that. So, this is the principle. Very important point, I think. And the people who like sophomore students in the university, college, I would be recommended to read like this book in Japanese written, translated version. Galliot's Fingers written by Peter Atkins, and in there there's the matter I just mentioned is written very collectively and concisely, and using pictorial expression, and from the history to the more sophisticated state-of-the-art concepts is written all over. This is evolution of science and scientists. So I'm not. I was not good at the grade at the university, or grade of physical chemistry, structural chemistry, because I think I made a mistake, simple elementary mistake, uh, uh, human from a human error, from my restrained concept or procedures. So, but the concept I understand is from this textbook, but the textbook doesn't exist at that lecture for structural chemistry or physical chemistry in sophomore grade or in 1997 or so. In 1997 and 1998, and it's I had very little time to study on my own in my own time framework, because I had been working for delivery person of the newspaper shop, uh, deliver paper delivering job, paper boy, paper boy on girl, for paper boys and girl to living in a shop, and just at the same time the university students in these days, and I've been working almost 6 to 7 hours a day, other than commuting, not commuting, go to college to listen to some lectures. So it's not enough time to, and I wanted to read this book at the lecture, and I prefer the lecturers of these kind use this Atkins textbook directly. But of course, lecturers are professional researchers and lecturers, and they have their concepts to teach, and so my attitude was wrong at that time, but my fabric or my tendency to what I like or what I dislike is somehow deviated, and I got less grade I expected, and it was my fault. But I prefer and I recommend this textbook for sophomore grades, and also this book. But I didn't find, I've never find in this book the original in English version in Tokyo. What's the name of this in English? This is very good. Also, this is very good and very too much to read for usual human being. But I think it should be read using a lot of times. Taking a lot of time, you take your life to read this book. Is good. It's worth reading in our life, bit by bit. It's so interesting, and you got some intuition from this book, maybe. and also for sophomores this, and to run physical chemistry this. And why I pick up these is the to congratulate Roger Penrose and to go back to the some elemental intention for to run or to act, to access the nature, which is road to reality of yourself, in the aspect of the philosophy. And finally, I'd like to use this text to find out why. Why 4KT R or Y 4KT gamma equals 0.666 which is two stars, gamma times Gm, or or voltage squared for current, noise squared, and amp squared per hertz, volt still squared per hertz. Why this? Why this? Or OKT gamma over R, or OKT no gamma, OKT over or OKT gamma over GM. For resistor, MOSFETs, for MOSFET and resistor, voltage power, noise power, current noise power. Why 4KT register something for voltage power? I'd like to check why. Of course, many people remember when to get the RMS noise, RF noise, and compare the oscilloscope noise. We need Vn equals square root 4KTR for resistor. For measuring resistor noise, using this to get RMS value, voltage RMS, microvoltage RMS. Using this and using this times the bandwidth, total noise, microvoltage RMS. Just remembering, but why? To get why, I don't know why now exactly, but I know, or every high school student of science knows, that one molecule, ideal molecule, has moving freedom of something, freedom of dimension in three-dimensional z, x, y, or z, y, x, of for one dimension half of kT, and for three dimension 3/2 kT joules of energy. And from this, adapting, accompanied with concept of Boltzmann, no, not Boltzmann constant and temperature using, and also Avogadro number 6.02 times 10 to the 23 molecules in 1 mole per 1 mole, and find out pressure times the volume of the gas molecule, corrective groups of molecule, ideal molecule equals a very simple way. The number of particles, molecules in mole units, mole times constant capital R times temperature T, or K, which is PV equal K T energy. Oh, I forgot that. I remember, and all students of high school remember this. PV equal nRT, and this is related to this three-dimensional single ideal molecule energy and pressure. Very simple model, using very simple model to get this, using this. And why one molecule is from Planck, from Planck's or Boltzmann's this description of the nature to Tokei 力学 Tokei in English, but I forgot. Tokei mathematics, mechanic, thermal, statistical, statistics. Groups of molecules appear, generate this kind of behavior. We generate the behavior described this value 1/2 kT. K Boltzmann constant 1.38 times 10 to the minus 20, 18, 21, 23 watt joule per Kelvin. KT's temperature in Kelvin 273 point something degrees Celsius, minus this is 0 Kelvin. 0 Kelvin, 0 degrees Celsius equal 273 Kelvin. So 27 degrees Celsius, of course 300 Kelvin approximately. All students need know this in Kelvin, and maybe students know this 1.8 something Boltzmann constant, and this is Joule. This Joule energy is appears here again, accompanied by R and making voltage noise power, average power. Why an average? An average means in consistent with statistical property. Average. Where? Okay, average. Average. averaging, operation of averaging in statistical mechanics, statistical thought, statistical properties is by averaging. Using averaging, we get KT representation of molecular energy, and this appears statistically averaged particle property of KT accompanied by R makes voltage noise average power. That's why in register connected to nothing. There's a close temperature, ambient temperature, or ambient temperature, and temperature on silicon. There's poly resistor, and there's a insurance non-connected non-conductive matters like SiO2 and this polysilicon, and polysilicon register, poly register R poly of values of R ohms makes voltage noise of 4 kTr on average by power per hertz, and it's white and evenly dispersed in frequency. Why? On temperature. Temperature up here is T Kelvin, not ambient on silicon. That's kind of introducing some errors to utilize ambient or cheap junction temperature. Its junction temperature to describe must be used for these noise calculation, thermal calculation. Junction temperature needed. Ambient temperature 30 degrees Celsius. Junction temperature 50 degrees or more, sometimes for around 50. So the noise expected from ambience is less than actually produced noise on chip and on the system signals. The temperature introduces the voltage. So we call this summer voltage, summer noise, and quicker noise and short noise is different. The cause of summer noise and like 4 kTr, 4 kT gamma GM, or in current 4 kT gamma over GM gate referred voltage, and 4 kT over R equivalent current noise of resistor is what? What do I like to say? Is thermal noise introduced by temperature. Temperature means what the temperature means. We need to learn from physical chemistry or physics or statistical physics or thermal mechanics, statistical mechanics. By the way, what's the Boltzmann constant? I'd like to check again the Boltzmann constant 10 to the what? Of course, we can re-engineer the exponent. What's the exponent of it? First look at the physical chemistry of, written by Atkins. I have 6th edition, older edition. And there's, of course, there's K here. Boltzmann constant is mandate to remember for scientists, but circuit engineer like me sometimes forget not using K directly. K is, but I know what's K. K appears in page 19, page 20, 21. No, 22, 23, 4. Molecule movement. Velocity squared, square root of velocity squared. Kinetic model of gases. He starts the gas laws from looking at the ideal gas into statistical group movements like PV equal nRT. This is chemistry. And kinetic model gas are used after that. Use this PV equal nRT. After that, kinetic model is derived, and maybe from here appear in Boltzmann constant K. 22nd, 28. There. Collision frequency 29. KT appears 28 in 28. KT appears in 28. Why? Accidentally happened 20 in 28. 28. Before 28, I don't see any K. No quantization of energy in there's quantization energy, page 5. Page 5 ideal gas constant. What's constant? Gas constant. The gas constant, capital R, gas constant, the gas constant R equal K Na or NaK. Na equal Avogadro number, and K is Boltzmann constant. Which is the same, 23. I was right. But minus. Okay, 0 per Kelvin. 23 is right. It's weird. Inverse of. But it's easy to remember utilizing this. Remembering this, gas constant is Kna, K equal 10 to the minus 23, and Na equals 6.2. This is by this. Na equals this. What Na? By this, Na equals written as the same. 6.02 times 10 to the 23rd, 10 to the minus plus. Cancel out, and this is just a number, or maybe 1/5, nearly 1/5. No. one nearly 6 point, nearly 7, さあ4、四六二十四、四六二十四、8, nearly 8. We remember 8 point something. This is just 8, approximately 8. The gas constant, approximately, okay? Approximately 8 joule per Kelvin. N equals just a number, and this is joule per Kelvin. Approximately 8 joule per Kelvin is the gas constant, and the Boltzmann constant is the inverse of the Avogadro numbers. So remember, this is very useful to remind the exponent, because we all know Boltzmann, the Avogadro numbers, including how much exponent, 10 to the 23rd, so 20 to the minus 23rd is reasonable in reality, but this is reality. One of the roads to reality, number 8. We know nature by numbers and by numbers in scientific way. Of course, we sense temperature, and we sense the wavelength of the light and color, and that's not enough, never be enough. By color and temperature feeling, it's never enough for science and understanding the nature, and it's not good road to the nature, road to the reality. Reality suffers. We suffer the reality aspects of misunderstanding. If we need just sight and feeling of the nature appear around here, environments, it's misleading behavior. Just doing like that, we need numbers. So one road to the nature is the gas constant. R equals KNA, and Kn sub A, N sub A 6.0202 times 10 to the minus 23rd, and Boltzmann constant K sub B or K equals 1.38. Okay, 2 times 10 to the minus 23rd, and R equals K times N sub A, capital N sub A, equals approximately 8 joule per Kelvin. Calculator. I don't have calculator here. 360、326、2、0、48、318、66、8.3008 something, near equals more accurately 8.31. This is approximately nearly the integer 8. So capital R, the gas constant, is very useful to remember, reminding the Boltzmann constant. We again and again learned in high school or junior high school. No junior high school. In high school, this is 10 to the 23rd. A lot of molecules, just in a centimeter. In usual temperature. K, and so K is Boltzmann constant. Uh, the value is this. The number is this, and PV equal RT. KNAT. Maybe I'd like to check. PV equal RT. PV equal RT. So this textbook starts with quantum mechanical concepts. And in equilibrium of gas, the property of the gas appears in PV equal capital RT, no, of course nRT, and one more, and then more nRT. And R is in Joule per Kelvin, approximately 8. Then R, then nRT, R equal KV, KNA. And what's the energy or kinetic energy of one molecule in 3 dimension appears, here. Kinetics, physical transfer of pure substances. Reaction, molecule, gas, and contents. See, contents of 6 emission, equilibrium, structure, equilibrium structure change, introduction, equilibrium structure change, equilibrium. Micro expression representation connect to the equilibrium corrective matter behavior. Corrective behavior of particles from micro, bit by bit, molecules movements. And the molecule movements look like having 3/2 kT joules of energy at temperature T, ideally, and Y. This is known as another style, boil and shower. So and more molecular vision included nRT. PV constant, PV constant, TOV constant. This is Char and this is Boyle. And Boyle Char and accompanied with molecular concepts. So you understand, molecular aspect is up here, around here. We get molecular concept more reality only when we dealing with tekite in chemistry. What tekite? I don't remember. Disseparation? No. One property. Judge to find out some property, molecular property, Chuwa tekite in Japanese, or Sanka Kangen tekite makes us to feel the sense of molecular words. Molecule in liquid. Liquid consists of molecules. We find out that the road to reality is the Chuwa tekite or Sanka Kangen tekite redox, oxidation and reduction tekite. What kind of tekite? In English, I don't know. But it's the another case, another type of sense molecule words. Matters consist of molecules, actually. So these experiments very important. Experience these is mandate for scientists in high school. So unfortunately I didn't myself do this, but in university again I had fortunate opportunity to make it done, and so one more road to reality, to sense the world. What appear is the kind of this pi orbital makes these molecules like an antenna, and in resonance the electron captures the energy of light, and the light is the color of these molecules, polymers, or these molecules, or solution of molecules. These molecules appears looking in the color of red or blue or green. The complementary color of the incidental. Incidental color is white, and all of the elements of the wavelengths from 400 to 800 nanometers, and this is scattering and going into our eyes, but without absorbed elements of wavelengths. If red is absorbed, we look at these solutions, blue kind of liquids. From this we model these molecules. We know that what in chemistry, by chemistry, what kind of solution and what molecules is existing in the liquid, and modeling these molecules in using quantum mechanics simply, and capturing the right observation absorption, and making spectrum and watching the numbers. Watching the numbers, we can calculate the Rydberg constant or Planck constant. And Planck constant from this simple experiment using spectrometer and calculating some calculation is very precise in definition is the same in the sixth or seventh order. Sixth or seventh order of the same value of the precise definition of Planck constants using quantum mechanics. Used by quantum mechanics. Quantum properties of matters makes us understanding the reality of the nature, quantum reality of the nature, from quantum Planck constant. So the Planck constant derived from this experiment nearly the same as the exact, the most precise definition. Just a simple experiment and just simple observation and simple calculation makes us understand, realize, know the Planck constant. And this is one aspect of another aspect of the road to reality. 脱線してしまう。そしてだらだら脱線してしまいますが、this doesn't appear. Half KT doesn't appear here. But Galileo, the 10 Great Ideas of Science and Galileo's Finger by Peter Sims. Does this have KT expression? Quantum. Simplifying understanding quantum. Kinetic energy of molecule is, in a sense of statistical sense, averaged one molecule on average have 3 half kT of kinetic energy, total energy, almost kinetic energy. That is gas. Gas means very separated molecules, the constituent. The distances, but the interference could be neglected. So potential energy approaches like that, 0, and we have only the kinetic energy. kinetic energy. 1, 2, 1 molecule, 1 molecule, 2 separated enough, having neglectable potential energy in each other. These interaction, repulsion and repulsion, indioku, impressive, or what's the indioku in English? 気力はrepulsion, pulsion, impulse の引力 force, central forced 向心力、central force 引力 but 引力 and 気力 doesn't appear here. Length is separated enough is a gas, ideal gas. So this is 3.5 kT approximately in a statistical manner on average, and kT appears like that. The K is this from 8 joule per Kelvin. Gas content constant PV equal T, we all know from science students, or everybody know. And dimensionally, dimension analysis. Joule called Newton meter. Joule second is Joule second. Watt second equals Joule. Watt equals Joule per second. Watt TT. Joule, Newton, meter, and second. And this is for energy, watt is for power. Energy generated or consumed in a second. And kT is in joule. Joule per second and joule per Kelvin times Kelvin. K equals 1.38 times 10 to the minus 23rd joule per Kelvin. T temperature in Kelvin. The 4 kT, and R is the resistance, ohm. And power, like I square R or IV or B square over R is power. Resistor consumes current applied I. This is IV, and some energy released from this resistor. I square, why I square IV equals the power is the next thing we'd like to check, but usually use these very used to, we are used to, more used to than 4KTR. Whenever squared of register in volt square per hertz. And what is OKTR? OKTR is volt square per hertz. Hertz equals, in dimension, 1/2. Like 60 hertz, we mean 60 circulation in a second. For frequency, the inverse of frequency means period. Periods, peripheral, period. Periods, period, I forgot. This is period, not period. Maybe this is period. 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 おかしいな。period. Purio, not period. Sorry. Maybe period. T. Now this T is not temperature. Inverse of frequency. This is seconds, in seconds, dimension of seconds. So we got, if the coincidence, to check coincidence, we need to time some frequency bandwidth in hertz, and this is total power of, this is total power integrated power in volt scale. Volt scale not power, but this average value, and it average value volt square, and volt square divided by resistance makes this power. This, if divided by R, this cancelled, and this is from this is 4KT delta F equals power. And if this is power, this is in watt, but joule per second. Of course, this is joule and this is per second. There's consistency of 4KTR and joule. So KT equal energy and R resistor, and in any resistance we can get the power, average total power of noise from dividing this, but this is actual power, heat. This is heat generates from noise, and because noise is random movement of electron or holes, carriers moving backward and back and forward, randomly, random movement, random motion of carriers. Carriers. It generates some heat, small heat, which is by noise, and it make equivalent equilibrium. What's equilibrium? But equilibrium and the spelling of equilibrium is from here. We can check from here. Or you say, hey Siri, what's equilibrium? って言ったら、it comes up here. Equilibrium, what? Equilibrium. So, equilibrium. Equilibrium. 平行状態。Surrounding and matter, the heat incoming and outgoing is balanced. And the energy heat is it. All students in high school knows heat is one aspect of the energy. Motion to heat, heat to motion. Kinetic energy to heat energy, and it's all balanced in the surface between this. 境界。イクイリブリウム、イクイリブリウム、イクイリブリウム。OK。Equilibrium. In equilibrium, we got 4 kTr, or noise power per hertz. Kt is Joule. This energy is kinetic energy, from random motion of carriers, in this case electrons. If there's a if this is a poly or